Hello, this is Mr. Sorrentino here again, doing another Math 31 video, and this one is working on 5.4 properties of logarithmic functions. And one of the properties we were sort of introduced to in the previous lesson, and basically that's the one where we can show that if we have a log base a of a to the x, where the logarithm and the exponential base are right next to each other, means nothing in that space between them, then they just cancel out, leaving the exponent. It works the same way too if you have an exponential raised to a logarithmic base. Again, as long as there's nothing in between them, then they cancel each other out, leaving me with the x right there. So in the instance of these three examples here, they're pretty easy, because log base 5 next to an exponential base 5, this and this cancels. I'm left with 2. This is the same thing as 10 raised to the log base 10 of a. No logarithmic base reported. We automatically assume it's base 10. And again, an exponential base 10 and a logarithm with a base 10 next to each other cancel. I'm left with a. And of course, this is the same thing as log base e of e to the s. And again, same instance here. They just cancel, leaving me with s. So those are pretty straightforward, and that's when we were dealing with situations when we were trying to evaluate logarithms that were actually powers of the given base. We kind of use that and solve for that. This is just a shortcut for that process. Now, if I have other things in between the logarithm and the exponential in some way, I have to deal with that and work with that appropriately. And that's what we're going to be looking at mainly in this lesson is, okay, what if we have a situation when we have maybe, instead of a 10 to the log a power, we have 10 to the 2 times log a power, how we handle that. Or if we have for the log base 5 of 5 squared minus 5. How do we handle that if we can handle that? Or maybe it's better to handle it this way, say 5 cubed, or there's going to be different variations that we could possibly deal with in order to hopefully take care of this and come up with an approximation or make our lives easier. So we're going to learn about these properties as we go along with them. Now, as we go into these properties, you're going to see that we have basically what leads up and allows us to make the rule for this, letting x be the log base a of m, letting y equal to be the log base a of n, and putting these together and kind of showing how the exponential rule applies and creating this logarithmic property. But, ultimately you're just responsible for knowing the properties, so don't feel obliged to know how this proof all works. You just have to know what the property is. And so for the first property, and these properties you should know forwards and backwards, because we're going to make use of them in both ways. So this was the product property, which means if I have the sum, notice I have the sum over here of 2 logs of the same base, then I can rewrite that as the log of that base times the product of the two things being logarithmed. I guess I could use that as a word. And likewise, if I have a logarithm of a product, I can write that as the sum of 2 separate logarithms, and the 2 separate logarithms are of the 2 or more things that are being multiplied together before the logarithm's happening. So the next one deals with the quotient property. The quotient property, subtracting 2 logarithms of the same base, should equal the quotient of the 2. Please keep in mind, I'll have students that will look at this idea right here and want to say this is log base a of m over log base a of n. Again, kind of distributing that logarithm, but you have to remember this would be what the log of base n of m is. That's not the same thing as this being subtracted. So, don't get them confused. Don't get the change of base formula confused with the quotient property. The quotient property says if I have a single logarithm of a quotient, then I could basically go this other direction here and make it a difference. If I have a logarithm of a base divided by a logarithm of the same base of two separate things, then I can rewrite that as a single logarithm this way. And it's going to be important for us to be able to know, if we want to write things as a single logarithm, what we need to have in front of us to do that. The last one that we make a lot of use of as well is the power property. The power property says if I'm taking the log base a of something raised to a power, so basically I'm taking the log base a of an exponential, then all I need to do is take the exponent and move it in front of the logarithm and make it a multiplication. So these are the three properties that you're being introduced to in this particular section, and basically these examples are going to kind of walk us through how to make use of these examples. So let's have a look at example 2. Here you're asked to express each of the following as sums and or differences of logarithms. If we rewrite a here, the log base a of x to the fifth y to the fourth over z cubed. Zoom that back in a little bit. I first notice I do have a quotient, and so I have x to the fifth y to the fourth divided by z cubed. According to the quotient property, applying it in the reverse that I seen it presented to me, I can rewrite this as log base a of x to the fifth times y to the fourth minus log base a of z cubed. And at this stage, technically, you should really have this in parentheses, but you really don't have to have them in parentheses. When you get expressions that have multiple terms involved, quantities, the parentheses need to be put in there. Still not quite done yet, because this here can be split up some more. And I can split that up by saying, well, by the product property, I'm going to have log base a. Since there's a product in there, I'm going to have x to the fifth plus the log base a of y to the fourth minus the log base a of z cubed. And a lot of students might think that that's good enough for this, but the way the textbook is written and the way what's usually expected of this is that you're asked to show something that shows sums and or differences of logarithms, nothing with anything raised to a power. So each one of these three terms here, term 1, term 2, and term 3, can be rewritten one more time by moving each one of these exponents to the front and making it a multiplication. So I can call this 5 times the log base a of x plus 4 times the log base a of y minus 3 times the log base a of z. And that would be the fully written answer as far as the textbook is concerned. So b, I'm doing the log base b of m squared over n times p to the fourth to the 1/2 power. That's what the square root's doing. And so to really make this a little easier, I'm going to square root everything first. And that means that each one of these exponents, knowing that there's a 1 here for the n, it's going to get multiplied by 1/2. So I'm going to have the log base b of m to the first power. N is going to be to the 1/2 power. And of course, p is just going to be p squared. Again, I have a quotient, so I can rewrite this as the log base b of m minus the log base b of n to the 1/2 times p squared. And here's why I have to be careful with this, because this logarithm is going to become a sum, but this sum is being multiplied by -1. So in this instance here, I'm going to have minus the quantity, the log base b of n to the 1/2 power plus the log base b of p squared. But this negative has to be distributed. So I'm going to have the log base b of m minus the log base b of n to the 1/2 minus the log base b of p squared. And then, of course, lastly, the second and third logarithms in this expression have exponents, and for this to be considered complete, I shouldn't have any exponents. I should just have sums or differences of logarithms. So I'm going to have, this stays the same because there's no power on that m, minus 1/2 the logarithm of base b of n, minus the logarithm base b, well, 2 times that logarithm base b of p. And that would be your final answer for that one. Now, one type of problem they make use of this with, this idea, is that what if you have a situation like the following? And this is kind of what you had to do back in the old days. Logarithms were taught at one point in time, not that long ago, mind you. We didn't have calculators that could compute them. There was no log button or natural log button on the calculator. We had a table of logarithms, and they were just base 10, so if we had to do any other base, we had to use the change of base formula to convert it. And then if we had numbers that didn't fall on that table, we had to use these rules to convert it to something that would be on this table. So for instance, here you're given that the log base a of 2 equals 0.7565. The log base a of 3 is 1.1990. And you're told that the log base a of 5 is 1.7565. You're asked to find the following. And it should actually say here without use of the calculator. And basically, you really shouldn't be able to do that with the calculator anyway, because you don't know what a is. I mean, so you can't even put that in. So this is basically one you can't use the calculator to do. So what I'm looking at this here is like, well, I don't have 25, but what I do have is that this is the log base a of 5 squared, which we know from our from our power property, that's going to be equal to 2 times the log base a of 5. So if I know what the log base a of 5 is, I could solve this problem, and I do know that. Here's an issue that I see a lot of students do with this type of problem. They're used to substituting numbers into a logarithm, so I'll have students that will say, okay, this is equal to the log base a of 1.7565. That's not the case. I mean, 5 and 1.7565 are not the same number. The log base a of 5 is 1.7565. So when I do the substitution, I'm substituting the 1.7565 in for that number only. And so that's going to be approximately equal to 2 times the quantity 1.7565, which is going to be equal to 3.513, and that would be the answer. So now we know what the log base a of 25 is. With the log base a of 10, well, I can again, I don't have that listed up here, but I can rewrite this as the log base a of 5 times 2, because 5 times 2 is 10. So I'm going to have the log base a of 2 plus the log base a of 5, because a product becomes an addition of logarithms. And that's going to be 0.7565 plus 1.7565, 2.513. Sometimes they get a little tricky with these. For instance, this one here, 0.6. You might say, well, how am I going to do this one? Well, yeah, I could say, well, that's the same thing as 6 over 10. I do know the logarithm of 10, base a. But I can even say, okay, well, even in lower terms, this is the log base a of 3/5, because 3/5 is the same thing as 6/10. And I do know what the log base 3 of base a of 3 is and log base a of 5 is. With the quotient property, this is the same thing as the log base a of 3 minus the log base a of 5. which is going to give me 1.1990 minus 1.7565, but that ends up being negative 0.5575. And then D is actually a lot easier if you think about what it's saying. I mean, yeah, you could sit here and say, well, that's equal to the log base A of maybe 2 divided by 2, or you could say 3 divided by 3, or 5 divided by 5. It doesn't really matter. And then use the quotient property. But we know, just from going back to our experience with this, if I simply rewrite this, just call this side x, and say, okay, a to the x equals 1. Well, what power of a is going to give me 1? Well, there's only, I mean, it doesn't matter what the base is. The only exponent that's going to give you a 1 is if x equals 0. So the log base a of 1 equals 0. I mean, it doesn't matter what you have here as the base. If I have any logarithm of 1, it's going to be 0, regardless of what the base is. But as I said, the next thing we're going to be looking at is instances where, like example 4, where now I have a logarithmic statement that's written out in the expanded form, where it's written as the sum and differences of logarithms. Now they want us to put it back into a single logarithmic statement. This is going to become very important for us to do when we start solving logarithmic equations. So it is an important concept to get the hang of. I have the 2 times the log base x of a plus 4 times the log base x of b minus 7 times the log base x of c. Now again, this is a problem you could not do on your calculator. I want to write it as a single logarithmic statement, which means that I should just have log base x of something, and that's it. So I want it to look like that. So I'm going to start using some of these properties. Now I'm going to be using them in reverse than the ones I had done in the previous problems. I have these multiplication of 2 in front of this logarithm. I have the multiplication of 4 in front of this logarithm. I have a multiplication of 7 in front of that logarithm. I remember that if I had a logarithm of something raised to a power, that exponent became a constant being multiplied to the logarithm. And vice versa, if I have a constant being multiplied to the logarithm, these are going to become exponents on the respective things that the logarithm is affecting. So this is going to become the log base x of a squared plus the log base x of b to the 4th minus the log base x of c to the 7th. Now what I'm going to do is look at this and say, okay, well, I'm going to look at the sum first. Still following my order of operations. I still move from left to right when I have additions, subtractions. Remember, logarithming is its own function. It's its own parenthesis. I don't know what a is, so I can't tell you. I can't actually compute what a squared, b squared, and c to the 7th are. And I certainly can't take a logarithm of them because I don't know what the base is, let alone what a squared actually equals either. So I'm going to try to do the addition next. And according to the product property, if I have the sum of 2 separate logarithms, that equals the logarithm of the same base of the product of the 2 terms. So I went from having 3 logarithmic statements down to 2 logarithmic statements. And now I still want to get it down to a single logarithmic statement. So notice that I have this subtraction here of 2 logarithms of the same base, which means I could apply the quotient property, which would say that I can rewrite that as the log base x of a squared b to the 4th, which would be the term in front there, over c to the 7th. And now it's written as a single logarithmic statement, and that's what I wanted. Example 5, which is kind of similar to example 1, except we're dealing with situations now, as I mentioned before. For a, for instance, I have the log base q of the square root of q cubed. If I had the log base q and the q right next to each other, things would cancel, I'd be done. But unfortunately, this symbol is running between them. So I can't do anything with that yet. I can't just cause that thing to cancel. So there's a couple things I can do with this. When I look at this, Well, q to the third power square rooted is the same thing as me saying the log base q of q to the 3 raised to the 1/2 power, which is the log base q of q to the 3/2 power. Now, as we've done in example 1, having a log base q now right next to a exponential base q with nothing between the two would cancel them out, but just for the sake of argument, let's take this one extra step even though we don't really have to. I mean, I can rewrite this as 3/2 times the log base q of q. And if you think about it, well, if I'm basically looking at this statement here and say, okay, what power of q gives me q? Well, the first power of q gives me q, so technically that's times 1, which equals the 3/2. So that's kind of more of an explanation as to why the cancellation does work. It's because of that, ultimately because of that that power property, why you can do that. For b, I don't have a situation yet where the b exponential base and the logarithm base b are right next to each other. This 3 in front of the logarithm is kind of blocking, is in between them, and prevents me just from doing a cancellation. Well, I gotta get that 3 from between the b and log base b. So looking at this statement right here, having that 3 in front, I can rewrite that as me having b to the log base b of 2x to the third power. Now I have nothing between these two, and I would get my cancellation. So I had the quantity of 2x cubed. And if I'm going to simplify it, I really should just cube both terms in there. So 2 cubed is 8. This ends up being 8x cubed. The natural log of e to the x squared raised to the 4th power. The natural log, or log base e, if you want to just, again, think of it as being this, are not right next to each other. I do have this pesky parenthesis right in the way there. Now, there's instances where I really don't need to have that parenthesis, because you could say, well, Mr. Sorrentino, if I had log base e of, e like this, then, I could do that cancellation. Well, there, the parentheses really aren't needed. Here they are, because I do have this quantity being raised to the 4th power. If I just drop the parentheses, I do not have the same thing. So what I have to do with this is I have to get rid of this exponent of 4, so I am allowed to drop the parentheses. So I can rewrite this as 4 times the log base e of e to the x squared power. Now what happens is, now I have the log base e next to the exponential base e with nothing between them. There's nothing there. So now they do cancel. I end up with 4 times x squared, which is, of course, is 4x squared. Section 5.5, solving exponential equations and logarithmic equations. This is where we're going to start making use of some of those logarithmic properties we learned, as well as some exponent rules you learned in the past. And essentially another skill that we're going to be making use of is the fact that I can rewrite a logarithmic statement or an exponential statement into an equivalent logarithmic statement. Because generally that's what I do if I'm encountered with an equation that's exponential and I don't know offhand what the number is going to be, unless I see something like 3 to the x power equals 9, then I say, well, I know that 3 squared equals 9, so that's easy, x equals 2. But if I start to say, okay, well, 3 to the x power equals 17, I run into a difficulty there. And basically to solve that, I should rewrite that as the equivalent logarithm and then go from there. Likewise with the logarithm, if I rewrite it as an exponential statement, it might make more sense, and I'll be able to figure out what's going on with it just by plugging it into my calculator or, knowing my powers well. But there's going to be complications as we move along with this, and as we go through these examples, hopefully you'll see how some of these complications need to be handled so that you can start practicing and handling it yourself. There's another key point that they bring up here, and it's just most students figure this part out on their own, but it's good. It's worth saying. If I have the same base raised to what is represented as two different powers, if I have two different variables of this and I say they're equal to each other, that means, well, those exponents have to be equal to each other. So that stands to reason. And if I do a log of the same base to two things and they're equal to each other, but I have two different variables represented, that means that those two things have to equal each other as well. So this premise for the logarithm in particular is becoming very important, because notice that I can drop those logarithms as long as I have a single logarithmic statement on the left and a single logarithmic statement on the right. And I can rewrite a logarithmic statement as an exponential statement as long as I have a single logarithmic statement that I'm doing that for. When I start having multiple logarithm statements together, being added or subtracted or things like that, that's where things go awry, and I have to start using some of those properties as we move along. And one last thing, because if I have values that won't work with them, when I start solving these equations, I have the potential for extraneous solutions, because for me to solve these, I have to work under the assumption that with this equation, both sides exist for me to do this. And so, especially the logarithmic equations, as they get more complicated, they're fraught full of potential extraneous solutions. So let's move on to the first example. These first ones are not extraordinarily difficult. A is pretty easy. B, not too much more difficult as long as you rewrite it correctly. And when we get to C, a little bit more problematic, but you'll see is in the end not too bad. So 2 to the x power equals 8. This one is almost a no-brainer because most people do know their powers of 2. If you can sit here and say, okay, well, I know that 8 is 2 times 2 times 2, which is 2 cubed. Well, 2 to the x equals 2 cubed. And as mentioned above, if I have the same base and two different representations of the exponent, then those two things have to be equal to each other. So x equals 3 is the answer. That one's pretty straightforward. When I do the log base 5 of x equaling 3, well, as it looks right here, it's like, well, what number should I be putting in there? If you state it right, you say, okay, what number is equal to, gives me an exponent of 3 when I look at it as being a power of 5. That still might be a little bit difficult to put it in that kind of mannerism. So let's rewrite this as an exponential. So it's an equivalent exponential. This is going to be 5 to the third power equals x. And so x is going to be 5 times 5 times 5, which is 125. So again, pretty straightforward, not very difficult. Part C, not much more difficult. Now again, you have to make sure that you're at least following some basic equation solving techniques. Obviously, I want to get x alone on one side of the equation. I have a subtraction of 2 attached to it. I also have a logarithm base 7 attached to that quantity of x minus 2. Now, the log base 7 of the quantity of x minus 2 is more or less attached to those parentheses. Those parentheses are not going to go, the need for those parentheses is not going to go away, and therefore I just can't skip writing the parentheses until that logarithm is gone. And basically that minus 2 can't go away until the parentheses go away. So that lets me know what I need to take care of first in this instance. In this instance, that logarithm base 7 has to go. So what I have to do is say, okay, well, according to my rules that I have for this, I'm going to rewrite this as an exponential statement. So my exponential base will be 7. This is going to be the exponent, 7 to the first, equals x minus 2. Which is basically the same thing as saying x minus 2 equals 7. And then, of course, it's going to add 2 to both sides, and I get that x equals 9. And if you look back on it and say, well, for me to get a 1 on that side, if you know more about the logarithms, well, then 7 to the first power has to be what is on that side there, and that's what x minus 2 has to equal. So you can rewrite it as the exponential, get to the same point, whatever. So these are pretty straightforward and somewhat easy. The easier ones, don't really have much chance of having extraneous solutions, but you should always be aware that you should double check. log base 7 of 9 minus 2. Well, 9 minus 2 is 7, or 7 to the first. The log base 7 of 7 to the first is 1, so it does work. So it's not extraneous. As we get into more complex ones, like example 2, then you have to start looking a little bit more closely. Now, exponential equations don't tend to have as much of a chance of having extraneous solutions as the logarithmic ones. It's still worth your time to check them and make sure that they work. So let's head on to example 2. Now 3 to the 3x power equals 50. So again, it wouldn't be too bad if 50 was a power of 3. It isn't. I mean, I have my 3 to the 7th, my 3 to the 3rd power, which is 27, and I have my 3 to the 4th power, which is 81. Those, whatever 3x is going to be, it's probably going to be some sort of irrational number. And, that's going to make it a little bit more difficult. It's going to be an irrational number that's between, 3 and 4. But other than that, I don't have a specific knowledge of what that is unless I have to resort to using the calculator. So I am going to rewrite this as an equivalent logarithmic statement. So I'm going to have the log base 3 of 50 equaling 3x. How you want to handle it after this point is up to you, but make sure you're communicating what it is you're doing. If you have the ability to do a log base 3 of 50 on your calculator, by all means, just you can get the evaluation of that and say, okay, well, I would just divide both sides by 3 at that point and say, okay, there you go. However, if you don't have access to that or know how to get to that point on your calculator, or if your calculator doesn't even have it, to go further with this, I'd probably have to use the change of base formula to say, okay, that's going to be log base 10 of 50 over log base 10 of 3. And to get x alone, of course, I'm going to divide both sides by 3, which is the same thing as multiplying by 1/3. So I'm going to have the log of 50 divided by 3 times the log of 3. At this point, you can put it into your calculator. Make sure that you are putting it in correctly. Again, if you have a newer TI-84 calculator that has the newest operating system, you actually have a fraction bar command where you can clearly put what's on top and what's on bottom separate. If you're writing from left to right, please make sure as you do this that you're putting it into your calculator. If you're just going into your basic window and you're dividing by the quantity of 3 times the log of 3, because that multiplication is occurring specifically before that division occurs. If I carry through this, I get that x is approximately 1.1870. And again, to do a check on this, again with your calculator, do 3 to the 3 times 1.187 power. When I do that on my calculator, I get about 50.0067. So that's good enough. That kind of checks out for me that works, and I got a correct answer for this. And B, a little bit more difficult because I have an exponential on the left, I have an exponential on the right, and unfortunately they're not the same bases. If they're not the same bases, it's probably just best to interject a logarithm. And someone will say, well, should I use log base 5 or log base 3? And you could use either one of those, and that'd be fine. It's going to work really well on one side of the equation, not so well on the other. And on the side it doesn't work that well with, you might have to use a change of base formula anyway. The one nice thing about exponential equations, for me to solve them, I do ultimately have to use a logarithm, but I don't have to use any particular logarithm, as long as it's any logarithm. The best thing to do is just rewrite that, of doing the log of both sides. These have to be equal to each other because the two quantities themselves are equal to each other, so their logarithm should be equal. The reason why it's good to write it that way is because now I have these exponents. The issue with solving the equations that are exponential is getting those x's, or whatever the variable might be, out of the exponent and being written as bases. The only rule we have that helps us do that is the power property, which says that I can now rewrite this as x minus 1 times the log of 5 equals 2x times the log of 3. Where students have some difficulty with this is, they want to start evaluating and say, okay, the log of 5 is this, the log of 3 is this, put an approximation in. We're still awfully early in this solution process. If I'm putting numbers in and already rounding into 4 decimal places, then if I have a couple more steps to go, the next step I'm going to have some more stuff that needs to be done, and I'm going to be rounding yet again to 4 decimal places. And then the next step I'm going to be doing some more computations and again be rounding to 4 decimal places. And what sometimes happens in those instances is that whatever value of x I get, I start trying to check to see if I get the same quantity if I put that x into 5 to the x minus 1 power versus 3 to the 2x power. I end up seeing that the two answers look different enough to warrant confusion, mostly because of rounding errors and doing a little bit too much rounding along the way. So what I suggest doing, and it does take some practice for students to get in the hang of doing this, the log of 5 is a number. The log of 3 is a number. Just treat these as being numbers for the time being. I want to get x alone, but right now, for me to get x alone, I do have to manipulate a few things and do some operations to make that happen. If I treat these as numbers, then I'm going to have x times the log of 5 minus the log of 5 equaling, well, this one doesn't have much to do with this, 2x times the log of 3. I want to get all my x's on one side, and anything, this is log of 5, not log base 5. I'm going to get my x's all on one side and anything that doesn't have an x attached to it on the other side. I like having my variables on the left, so I would subtract 2x log 3 from both sides, and I would also add log 5 to both sides. And so what happens with those is that, I got a cancellation here, I have a cancellation here. So I have x times the log of 5 minus 2x times the log of 3 equaling the log of 5. Without me figuring out what log 5 is and log 3 is, I kind of lose my ability just to combine some like terms, because if I just had some number times x, and I actually wrote what the number is, and then some number times x times this 2 out here, I'd be able to carry through the subtraction and combine those like terms. Well, I'm doing it this way to keep this being as exact as possible. I kind of lose my ability to do that, but what I can do is I can factor out the x. And if I do that, I'm going to be left with x times the quantity log of 5 minus 2 times the log of 3 equaling the log of 5. And of course, this one here could be simplified a bit more by moving that 2 to the inside, and I would have x times the log of 5 minus the log of 3 squared, which would just be 9, equaling the log of 5. Since these both are numbers now, me subtracting them would produce yet another number. And so I do have x times a number equaling a number. So from a basic equation standpoint, all I really need to do now is just divide both sides by the log of 5 minus the log of 9. And scooching this down a little bit. That would leave me with x equaling the log of 5 over the log of 5 minus the log of 9. Please don't do any cancellation saying, well, I have a log 5 on top of a log 5 on bottom. This term here has no log 5s in them. You would not be able to cancel them. The other thing you would be able to do at this point is approximate this, and you get about negative 2.7381. The next one's a little bit more problematic because it's not just an exponential equation. And notice I do have exponentials, and they're base e at that. I'm going to have to do some work on this one. It's going to have a quadratic structure to it eventually, and we're going to have to handle that. And when I start taking functions that are exponential and start putting quadratic things into it, it gets, again, you have the possibility for some extraneous solutions along the way too. So we have to be on the mindful of that. Well, right now what we have here, and I'm going to rewrite this ever so slightly. I have e to the x power minus 24 over e to the x equals a negative 2. Certainly having an e to the x power makes things complicated enough. Having an e to the x power also in the denominator, which gives it some rational feel, not a good thing either. Makes it a little more complicated. Along with that, for me to convert an exponential equation into a logarithmic equation, I just have to have the format, in this case I'd have to have e to some power equals whatever's on this side here. I don't have that structure here. I have two exponential statements being added or subtracted together. I have to figure out a way to get to a point where I have something that looks more along the line of that at some point. So I have to play around with this a little bit. And the first thing I'm going to do on both sides of the equation, or to the whole equation for them, is just I'm going to multiply everything by e to the x. The reason being is I want to get rid of this denominator of e to the x. So here again is something we're starting to do operations on this equation, and I'm working under the assumption that everything here exists. Well, 24 over e to the x power could potentially, being that having some rationalness to it, could have extraneous solutions because of the fact that I'm making an assumption that could not exist. And so e to the x times e to the x is e to the x plus x, which would just be 2x. Of course, this becomes just a minus 24, and this I'm going to have negative 2 e to the x. I'm going to add 2e to the x to both sides. And so when I do that, I have e to the 2x minus 2e to the x minus 24 equaling 0. Although it's an exponential equation, it has exponential in it, and I'm trying to solve for an exponential base. It also has a quadratic structure to it, in that because this e to the 2x is the same thing as e to the x squared minus 2 e to the x. I'm just going to put parentheses around it kind of to emphasize them. I have something with involving the variable squared, minus 2 times something involving the variable that's not being squared, this is basically a quadratic format. It has a quadratic structure to it. And so for me to solve this, I can just go with the step and say, okay, well, I'm just going to and I can pick any letter of the alphabet I want. For the sake of argument, I'm just going to pick A to equal e to the x. Recognizing that, I'm going to turn this equation into something with a variable a, but ultimately I am looking for what x is. I need to keep that in mind, but I'm going to rewrite this now as a squared minus 2a minus 24 equals 0. And I'm going to use factoring, but if you use the quadratic formula or what have you, the solution for this isn't too bad, because this would factor into a minus 6 and a plus 4, which means that a minus 6 equals 0 or a plus 4 equals 0, getting back to that zero product principle. And so a would be 6 or a would equal -4. But again, I got answers for A. We're not looking for A, we're looking for X. A was something we put into the problem to help us be able to do some work with it, but it's not the answer. So I got to get the X back, and so I'm just going to go back and use this again and say, well, A is e to the X, so e to the X equals 6, or e to the X equals -4. Which the second one, I can automatically, right now, eliminate. E is a positive number. I cannot raise it to an exponent and get a negative. If you didn't see it there, the next step we would do is turn this into a logarithmic statement. And this one here would be x equals the natural log of 6. This one would be here that x equals the natural log of -4. And again, we can't do that one either, because we can't take the natural log of -4. So this is the one and only answer here. And so I could say that x equals the natural log of 6. With this one, I have 4 to the x minus 4 to the negative x over 4 to the x plus 4 to the negative x equaling 1/4. There's a lot of exponentials going on here. They're all base 4, which is nice, which means eventually I should be able to get this down to something where I could apply the logarithm properly and get an answer. But, especially if I rewrite it like this, which is what essentially it's the same thing. It's like saying 4 to the x minus 1 over 4 to the x over 4 to the x plus 1 over 4 to the x equals 1/4. That's just even uglier, but that's what the negative x powers mean. So now I have fractions with fractions in them. The reason why I wrote it that way is because it makes it a little bit more clear about one way I could possibly solve this, and that is simply to multiply the top and bottom of this by 4 to the x. I don't have to multiply both sides by 4 to the x. I don't have to do anything to the right-hand side. Here, multiplying by 4 to the x over 4 to the x is like multiplying by 1, so I'm not really changing the left-hand side. I'm just, making it a little bit easier to deal with. Because what I end up having here as a result of that is I'm going to have now 4 to the x times 4 to the x is going to give me 4 to the 2x minus 1 over 4 to the 2x plus 1. So it's already looking a little better. Now, knowing that I have basically these as quantities, I have a single fraction on the left and I have a single fraction on the right, I can cross multiply. So 4 to the 2x minus 1 times 4 is going to give me 4 times 4 to the 2x minus 1, and 1 times 4 to the 2x plus 1 is going to give me this over here. In order for me to start manipulating things around, I'm going to have to get rid of the parentheses on the left, which means that I'm going to more than likely have to distribute this. So for me to distribute that, for the 4, I have basically 4 to the 1 here. 4 to the 1 times 4 to the 2x, I would add the exponents. And so I'm going to have 4 to the 2x plus 1 minus 4 equals 4 to the 2x plus 1. If I add 4 to both sides and subtract away the 4 to the 2x from both sides, that would cause some cancellations here, this and this obviously. So I'm going to have 4 to the 2x plus 1 minus 4 to the 2x. Over here I'm going to have 5. The difficulty that we're having with this is that I have to figure out a way of getting this down to, a single exponential statement so I could eventually make this a logarithmic one. I can't turn what I have now into a logarithmic statement. I have multiple exponential statements on one side of this equation. I can't rewrite it. I don't have that structure yet. And here looking at the work in hindsight being 2020, might not, for this bottom one down here when I did this multiplication here, it would have been better just to write it as instead of having the 4 to the 2x plus 1, leaving it as 4 times 4 to the 2x, and this leaving that as 4 times 4 to the 2x. Because what I can do with this now is that, I have two terms of the 4 to the 2x being multiplied to it. Here's times a 1. And so I could do some factoring. I could factor out a 4 to the 2x, leaving me with a 4 here and a minus 1 here. Make myself a little bit more room. And so basically I have 3 times 4 to the 2x equals 5, which 4 to the 2x would equal a 5/3. Certainly looking a lot simpler now. So we're making progress. And now I do have a single exponential statement on the left-hand side equaling a number. So now I can rewrite this as an equivalent logarithmic statement, where I would say the log base 4 of 5/3 equals 2x, which means that x would equal the log base 4 of 5/3 all divided by 2. That would be a suitable full-blown answer. And again, if you have a calculator, you could do a log base 4 of 5/3. If you took this number and did log base 4 of 5/3 divided by 2 and put that value in for all the x's you saw in the original equation, it would work. Without a calculator that does that, though, you might have to break this down further to get a suitable answer with this. You could use properties and whatnot. I'm just going to use the change of base formula. I'm going to have x equals the log of 5/3 over the log of 4 all over 2. Of course, having this being divided by 2, that would just put a multiplication in the denominator. I can rewrite this as the log of 5 minus the log of 3. And this could be rewritten as the log of 16. Still written with logarithmic statements, but not quite as yucky. And something you could certainly put into your calculator. As I mentioned before, since logarithms have domain restrictions, here's where I run into more potential for extraneous solutions, because when I do the steps necessary to solve a logarithmic equation, I'm working under the assumption that the logarithm or logarithms that I'm trying to perform on the left-hand side or whatever side of the equation they may be on can actually exist and work, and they actually do produce something. And so when I look at log base 7 of x squared minus 2, there are some x values that would give me negatives or 0 in that quantity, and those I would not be able to do a log base 7 of. So that means that when I start carrying through other work here, I have to keep in mind for this that x squared minus 2 has to be greater than 0, which means that x squared has to be greater than 2, which means either x has to be less than negative 1.412, whatever it is, 414 or something, or x has to be greater than positive 1.414. This is approximately what the square root of 2 equals. Keeping that in mind, because if I get any answers that fall outside of this range of values, then I know that they're probably going to be extraneous. I need to throw them out. So I'd have the log base 7 of something equaling 1. I do have a single logarithmic statement on the left, so I can rewrite this as an exponential. So I can say 7 to the first power equals x squared minus 2. I could add 2 to both sides. X squared would equal 9, which means x would equal a plus or minus 3 when I take the square root of both sides. And I'll show that. or the plus or minus to come here. Now, don't automatically think that because something's negative, and I'm dealing with logarithms, that it cannot be an answer. I should plug both of these in. If I put the log base 7 of 3 squared minus 2, that's the log base 7 of 9 minus 2, which is 7, that equals 1. It works out. If I do the same thing with the negative 3, well, negative 3 squared also produces a positive 9. Positive 9 minus 2 is still 7. And I get the same conclusion. So both of these work, and they're both the solution. So this one did not have any extraneous solutions. That could happen. For B, now if B, let me scooch this over. If B had been the ln of, something equaling the ln of 3, I could just simply say, okay, get rid of those and say whatever's over here equals 3. That's if I only had a single logarithmic statement on the left and a single logarithmic statement on the right. I don't have that. I have 2 logarithmic statements on the left and 1 on the right, which means that for me to do this, I'm going to have to apply one of the properties. And on this side, I have a minus sign, which means I'm going to probably use the quotient property, which says that if I have the difference of 2 logarithms of the same base, then I can rewrite that as the logarithm of x over x minus 4. Now again, me even doing that operation is working under the assumption that that I'm producing values that would exist when I take their natural logs. X has to be greater than 0 for this one to work. X has to be greater than 4 for this to work. So to make the whole thing actually carry through, X has to be more than 4. If it's not more than 4, it would be extraneous. I need to throw it out. Now I do have a single logarithmic statement on the left, and I do have a single logarithmic statement on the right. So now these would cancel at this point. And so now I can rewrite the left-hand side as x over x minus 4 equaling 3. Now, if you remember from earlier in this course, this is now a rational equation. Rational equations also have extraneous solutions themselves. So, I would usually have to say at this point, okay, what's any issues I could have with this? And I would probably say that, well, x can't be 4 because that's going to create something on the left-hand side that's not going to exist. But me already having the fact that this has to be greater than 4, I don't have to make that statement again. I mean, we're already working under the premise that x has to be more than 4 for any of this stuff to go on. So any answer I get that isn't over 4 would have to be thrown out if that should ever happen. So as I go through this now, thinking of this as 3 over 1, I do my cross multiplication. I'm going to have x equaling 3 times x minus 4, which is going to be x equaling 3x minus 12. Subtract 3x from both sides, I get a minus 2x over here, negative 12. Divide both sides by negative 2. I get that x equals 6. So this comes out to be a really nice answer. And if I just go in and now put that in, the natural log of 6 minus the natural log of 2 equals the natural log of 3. 2 ways I can check that. I mean, I can actually put the values into a calculator. This side here ends up, when I carry through that subtraction and everything, I'm going to have 1.098 approximately, which is what natural log 3 is. Or I could use the fact that, well, that's according to the quotient property again, that's going to be 6 over 2. And 6 over 2, of course, is 3. So, I mean, so I don't need the calculator to check this one in particular because I can use the property to actually help me out with that one as well. And usually the answers that are integer and base is actually a little easier to handle with that. Moving on to the last one, part C. A little bit more problematic. I don't have any logarithmic statement on the right-hand side. So I just can't drop out logarithms, you know, in any sort of way with this problem the way it is. I have stuff with logarithms on one side equaling a number. Now, if I had the log base 20 of just one quantity equaling 1, I could handle that. I could deal with that just fine. Um, I could rewrite this as an exponential equation and then go from there to solve it. I don't have that though. I need to have a single logarithmic statement on the left-hand side before I can take what I have and rewrite it as an exponential equation. So I need to figure out a way of doing that. Luckily, I have the properties that we learned about in the previous lesson. And those properties say, by the product property, since I have this addition here, I can rewrite this as the log base 20 of x minus 7 times x plus 5, and that would equal 1. So now I do have a single logarithmic statement. Now again, all this is working under the assumption that this exists. I mean, so I have here for this logarithm to exist, x has to be more than 7, because if it's 7 or less, I'm going to have 0 or negatives, and I can't do that. Here, x has to be greater than -5. So for any answer to be considered for this, it has to be more than 7. If I end up with anything that falls below that, it's not an answer. So with this now, I can rewrite this as foiling this out. I'm going to have x squared minus 2x minus 35 equaling 1. Again, I have a single logarithmic statement here. I could have done this in the previous step, or combined steps, but now I can rewrite this as an exponential. 20 to the first power equals x squared minus 2x minus 35. I can subtract 20 from both sides, and I like having my stuff on the left, so I'm going to have x squared minus 2x minus 55 equaling 0. This is now a quadratic equation. So, and what you find out is that there's not many factors of 55 that are integer factors, and none of them really give you a difference of -2 or give you an answer of -2. So, I'm going to use the quadratic formula because I do have it set equal to 0. I'm going to have 2 plus or minus the square root of 4, which is what 2 squared is, minus 4 times 1 times a -55 all over 2 times 1. X is going to be 2 plus or minus the square root of 224 all over 2, which can be further simplified. I'm not writing an X up there. It can be further simplified into 2 plus or minus the square root of 16 times the square root of 14 all over 2, which gives me 2 plus or minus 4 square root 14, which means I'm going to have 1 plus or minus 2 square root of 14. So I do have two values here. X equals 1 plus 2 times the square root of 14, or x equals 1 minus 2 times the square root of 14. And these are the exact numbers. Now the thing is, I have to keep in mind now, okay, well, are any of these extraneous? I should make sure that they work, but are any of them extraneous? Luckily, most of the time with logarithmic equations, if they're able to be put into the logarithm and the logarithm can be done, it should work and it should be fine. If it can't, then that's extraneous. Okay. 1 plus 2 times the square root of 14 is a positive number, because 1's positive, 2 times the square root of 14 is a positive number. I'm great. Now the square root of 14 is somewhere between 3 and 4, closer to 4, like 3.7-ish. So if I do 1 minus 2 times 3.7-ish, I'm going to have a negative number. This is less than 0. If I have a number that's less than 0, I certainly cannot put it into the x minus 7 because I'm going to have a negative number being subtracted by 7, making it even more negative. So this one here is extraneous, making this the one and only answer. And if you do put it in, it does work. And that brings us to the end of this video. So if you have any additional questions, please make sure to bring them up in class or to see me during my office hours. Until I see you in one of those places or until the next video, I bid you a good day and I'll see you around.